Okay, cool. So we are now on LNL section 11, problem 2A. And problem 2A states determine the period of oscillation as a function of the energy when a particle of mass m moves in fields for which the potential energy is for A, U is equal to A absolute value of x to the n. So first things first is we need to determine our x1 and x2, which would be the turning points of the motion. This can be done by stating that when E equals U, there is no kinetic energy because the motion comes to a stop and then returns to the other position from there. So we can write it as E equals A absolute value of x to the n. Thus, our x is equal to E over A to the 1 over n. And same goes for our x2. So our x1 would be the negative variant of this, and our x2 would just be the positive variant, E over A to the 1 over n. So we can now set up our integral. Integral from x1 to x2 of dx over the square root of 2 over m e minus u. And this integrand is just a straight rearrangement of the energy equation. So taking our 2 over m outside, this would also be equal to dt, integral of dt. Now for our bounds for dt, as it is with the pendulum problem, it's also very similar. So when the motion is moving to its first position and then it moves back to its original position, that would just be twice the length of the period. So it would be integral from 0 to the period over 2. So we get that integral from x1 to x2 of dx, and I'm going to go ahead and take out my factor of m over 2 from here to the outside of the integrand. So I have dx over the square root of e minus u. And there's also parentheses here because it's being multiplied to the energy and the potential energy. So that's what allows me to take it out of the integrand. From there, rewriting, I get that this is equal to t over 2, moving the 2 to the other side, and rewriting it in terms of my u that I'm given. I get 2 square root of m over 2 integral from, and now I notice that this is a symmetric function. It's the same value, it's just positive and negative for my bounds. So instead of doing that, writing it from integral from x1 to x2, I will just multiply it by 2 and integrate from 0 to x2. So I now have integral from 0 to x2 of dx all being divided by, and if I write this expression inside of the square root as e minus a absolute value of x to the n, which is my potential function, I can also simplify it even more to get 4 square root of m over 2 integral from 0 to x2 of dx over, I'm going to factor out my e, so e1 minus a over e x to the n, all inside of a square root. And I'm doing this because if I make a substitution with a dummy variable y, I will have x equals e over a to the 1 over n y. So my dx is going to be e over a to the 1 over n dy. And if I move this e over a to the other side with x, I get a over e to the 1 over n, x is equal to y. And exponentiating both terms to the nth power, I would just get my term inside of here. Sorry, not there. I would get my term that is over here, which is exactly the substitution I would like to make. So I can now write this as 4 times the square root of m over 2e, factoring out this e right here, integral from 0. Now, when x equals 0, y must also equal 0 from this substitution here. And when x equals x2, which my x2 would be positive e over a to the 1 over n, from my turning points that I calculated earlier up here, I would just get that y is equal to 1. So I now have my integrand in terms of dy. So I have dy over the square root of 1 minus y to the n. And from here, I'm going to go ahead and actually write it as 4 times the square root of m over 2e times the integral from 0 to 1 of 1 minus y to the n to the minus 1/2 power dy. And if I make a second substitution here, where u equals y to the n, therefore my du equals ny to the n minus 1 dy. So solving for dy, I would get dy equals 1 over n times y to the minus n minus 1 du. And if I solve for y in terms of u to the 1 over n is equal to y, I would just get that this is equal to 1 over n u to the 1 over n minus 1 du equals dy. And now I can fully replace this back into my integrand. So I have 4 times the square root of m over 2e, integral from 0 to 1 of, I should also factor out my 1 over n, integral from 0 to 1 of u to the 1 over n minus 1 times 1 minus u to the minus 1/2, which was our previous term, du. And this is just an integral expression of the beta function. So beta of x and y is equal to the integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt. So here we can see that our x and y is 1 over n and 1. So this would be beta of 1 over n and 1 half, because 1 half minus 1 is negative 1 half. And this is also able to be written in terms of the gamma function, which would be gamma of 1 over n times gamma of 1 half divided by gamma of 1 over n plus 1 half. And we know that gamma of 1 half is famously known to be square root of pi. So this integrand can be expressed as gamma of 1 over n square root of pi divided by gamma of 1 over n plus 1 half. And thus completes problem A.